This is a short introduction to the talk. It is based on work with Joseph Benjeloun, and the paper is available on the archive. So the talk is about a family of algebras K of n, one for every positive integer n. And these algebras are closely related to the symmetric group Sn of all permutations of n objects, and in particular to the group algebras of Sn. So K of n is a subalgebra of the tensor product of two copies of C of Sn. K of n is the subspace of elements in C of Sn tensor C of Sn, which obey this equation here for all gamma in Sn. K of n is closely related to ribbon graphs. The dimension of K of n is equal to the number of bipartite ribbon graphs with n edges. As I will explain in the talk, these are closely related in turn to the double line diagrams of large N gauge theory. There is a set of basis vectors E sub r, one for every bipartite ribbon graph for K of n. So arbitrary elements of K of n can be written as complex sum over ribbon graphs of E sub r with complex coefficients. K of n is also closely related to Kronecker coefficients. So the dimension of K of n is equal to the sum over triples of Young diagrams with n boxes of the square of the Kronecker coefficient. The relation between these two descriptions of K of n, one in terms of Kronecker coefficients and one in terms of bipartite ribbon graphs, is a Fourier transform on K of n, which is based on representation theory of Sn. A question in combinatoric representation theory has been, is there a construction of C or C square? Does C count some finite set of things? As we explain in the paper, there is an answer based on ribbon graphs. So a brief description of the answer. The integer linear combinations, so where we now restrict these coefficients to be integers, form a subspace inside K of n, which is in fact a lattice, which is described here. So we show that this lattice contains a sublattice of dimension, which is the square of the Kronecker coefficient for every triple of Young diagrams. How do we construct this sublattice? Well, this sublattice can be constructed as the null space of an integer matrix. For every triple of Young diagrams, there is an integer matrix, M sub R1, R2, R3. And you look for vectors V living inside K of n, which obey this equation. Now, it is a fact that null vectors of an integer matrix can themselves be chosen to be integer vectors. And there are integer matrix algorithms for constructing a basis of such vectors which obey this null vector condition. So therefore, in order to count C square, you just count the number of these distinct basis vectors and you get a set of things, the number of which is equal to C square. These matrices M, R1, R2, R3 are closely related to quantum mechanical systems on the algebra K of n. And in turn, these quantum mechanical systems have an interpretation in terms of quantum membranes. And this connection uses the link between bipartite ribbon graphs and Belly maps. So that's the end of the summary.